This will be a very quick homework help session for the Achieve problems. Section 2.3, like I think I mentioned in our notes, it's the most boring, easy section of the entire semester. And the reason these problems are boring is because, remember, anytime you're asked to find a limit of a function that is continuous and defined where the x value is approaching, then you just simply plug it in, and that's going to be the same. That's going to be the way for each of the problems in this section. So we'll go through them real quickly here. Let me go ahead, share my screen here with you. And this is my first problem on the Achieve system. Now, don't be confused by their very strange notation here saying using the basic limit laws as x approaches c of x to the p over q equals c to the p over q. All you got to understand there is just that, oh, okay, if x approaches c, then I can plug a c in for x. That's all you need to know. Same thing in the second one. The limit as x approaches c of k is just k. Why? Well, because there's no value of x to plug the c in, so for any constant, it's just that constant. Now, for our first problem here, and I'll just go ahead and bring this up for, in fact, all of our problems. Let's see here. Here we go. So when I'm looking at that first problem, it was the limit as x approaches 12 of x. You say, well, you know it's 12. Because if x is approaching 12, then the y value is approaching 12. You simply plug the 12 in. Same thing for the next one. It gave me the limit as x approaches 1 over 6 of x cubed. So I know that all I have to do there is plug the 1 over 6 in for x, and I can say, well, that's going to give me 1/6 to the third power. That's going to be 1 to the third, which is 1, over 6 to the third, which is 2/16. The third one here, it's always the same process. You just plug the value of x in because the function exists at that x value. So you can say, well, this is just 27 to the 2/3 power, which I'm wanting you to remember. That means the cube root of 27. Well, the cube root of 27 is 3. And then you're going to raise that to the second power to get 3 to the second is 9 for our final answer. Notice we're moving through these real quickly because these are easy problems in this section. The next one, you have a nice continuous linear function and you're asked what's the limit as x approaches 4. Well, the limit as x approaches 4 is the same thing as f of 4. Just 7 times 4 plus 2. We get our 28 plus 2 or 30. What about a polynomial function? Polynomial functions exist everywhere. So yet again, if I want to find the limit as x approaches 2, I should be able to just plug a -2 everywhere I see an x in this problem. So I do that. I have 2 times -2 to the 4th minus 5 times -2 cubed, and then plus 8 times -2. The first one, I know -2 to the 4th is a positive 16, times 2 is 32. So my first number is 32. Now, I'm going to have minus 5 times a -8. Well, that's going to give me plus 40. I have 32 plus 40 is 72. 72 minus 16, final answer of 56. And so now we're thinking, okay, this section is not bad at all, unless you just don't like the easy problems, then you'd say it's really bad. For number 6 here, we're supposed to plug a 5 into, again, it's the product of 2 polynomials. Well, the product of 2 polynomials is still continuous. And so I can say, well, then 5 exists in this function. And then the limit as x approaches 5 is simply the function evaluated at 5. We have 9 times 5 plus 7 times the group 2 times 5 squared minus 7. The first group gives me 45 plus 7 is 52. The second group gives me 50 minus 7 for 43. 42 times 43 give me 2,236. The next one, again, it's the product of 2 polynomials. This time they're both linear functions. I know I should just be able to plug the 1/5 in to find the limit as x approaches 1/5. When I do that in the first one, I would get 5 plus 1 for 6. In the second one, 35 divided by 5 is 7. 7 minus 1 is also 6. So I get the product of two 6's for my final answer of 36. For the next limit problem, they're actually giving us a rational function, but we know the only value that we can't just plug in this is where it's undefined at -3. So if I were asking you the limit as t approaches -3, you couldn't just simply plug it in. You'd have to either solve it numerically or graphically or possibly algebraically. But in this case, it's not approaching -3, it's approaching 5. This function exists no problem at 5. I just plug the 5 in. 10 minus 6 in the numerator gives me a 4. When I plug the 5 in the denominator, I get an 8. 4 over 8, we know, reduces to 1/2. The next one, I'll have the product of a linear function times, this is a radical function, that's the same thing as 6 on the root of x plus 1. Both of these would exist at x equals 1/36. So I can just plug the 1/36 in. When I do in that first one, it's going to give me 18/36, which is 1/2, plus 1. In the second one, when you plug in the 1/36, 1/36 to the 1/2 power, that's the same thing as the square root of 36, which is 6. 1/6. And then you'd have 6 times 1/6 gives you 1. You already had the other plus 1. So this just amounts to 1.5 times 2, which gave me a final answer of 3 here. So now, if I'm looking at number 10, I have a fraction with a radical in the denominator. I know as long as that denominator is not 0 or a negative inside the radical, this function would exist. So it's going to be fine to plug a 6 in. When I do, I would get 66 plus 9 on the inside. That gave me a 75 inside the radical. I'm betting that Achieve would accept the answer 1/75. I just wanted to make it look better and say, well, I know that the root of 75 could be broken into the square root of 25 times the square root of 3, and the square root of 25 is better written as 5 on the root of 3. So I put it as 1/5 root of 3. The next one is even quicker. It's just the limit as t approaches 6 of t to the -1. So we know that we plug a 6 in the place of t. You get 6 to the -1 power. You know that that's 1/6. No problem there. I like number 12. So we have a radical, a linear, and a quadratic all within a rational expression. So we say, well, all right, as long as the term inside the radical isn't a negative, and as long as the denominator isn't a value of 0, this problem should be fine to evaluate at 16. So we can. The square root of 16 is 4, so I get 6 times 4. And my second term in the numerator becomes minus 1/4 times 16, which is minus 4. My denominator, 16 minus 29, that'd be a -13, but that -13 is inside of a group squared. I know a negative squared is always a positive. 13 squared is 169. My numerator simplifies to be 24 minus 4 is just 20. So our final answer there, I'm not sure why I didn't circle it, but would be 20/169, final answer. For number 13, it gives me a quadratic function to a fractional exponent. And this should be okay as long as what the answer for this quadratic is not a negative number, because if it is, it'd be giving me an imaginary answer, because that denominator means that this is really a square root, and then you're taking that square root, raising it to the third power. In order to simplify to see what's on the inside, I go ahead and I plug the 15/2 in. I'll have 4 times 15/2 squared, that's 4 times 225/4, plus 8 times 15/2. I went ahead and wrote that as 60. I just said, well, 2 will go into 8 4 times. 4 times 15 is 60. Then I have the -1. Now I can see that that first term is, the 4's will cancel, and I'll just have 225. So I have 225 plus 60 is 285. Minus 1 is 284. Now I have 284 to the 3/2 power. And again, I'm betting you possibly could have entered that answer in to Achieve, but I didn't like it. I thought it was sloppy. So I thought, okay, how can I simplify this? I know that this part is a square root. So I automatically know that 4 is a factor of this. So you could say, well, 4 will go into 284 71 times. And I know that 71 doesn't have any further perfect square factors. So I could break this into the square root of 4 times the square root of 71, better written as 2 on the root of 71. And now that takes care of the denominator because I've taken the square root of all of that. Then I need to cube it. Well, when I cube this, I need to be thinking of, well, 2 cubed is 8. The square root of 71 cubed, that's the square root of 71 times the square root of 71 times the square root of 71. Well, 2 of those square roots of 71 multiply to just give me a 71, and then I have a third square root of 71. 8 times 71 simplified to be 568. Then I have my final answer there is 568 on that square root of 71. So now I can say, okay, final answer. And that answer is gorgeous. This answer would be, but I bet Achieve would accept it. For my number 14 question here, I have radicals within a fractional expression again. Limit as x approaches 5. I know that that's not going to create a 0 in the denominator. It's not going to create a negative in the term in the numerator, so this should be fine. You should be able to plug it in. When I do, your numerator becomes a 9. This is telling you to take the square root of 9. Well, that gives you a 3. In your denominator, 5 plus 3 is 8. This is saying take the cube root of 8, which is 2, and then square it. Well, 2 squared is 4. So I've got my final answer of 3/4 there. Now, for the last few questions here, let me go ahead and show this. This is number 15. They tell us to assume that the limit as x approaches 2 of f of x is -1, and that the limit as x approaches 2 of g of x is 3. And then it says, well, determine what the limit as x approaches 2 is of f of x times g of x. So what I did with that here, guys, is I just said, well, I know if the limit as x approaches 2 of f of x is -1, and the limit of f of x as x approaches 2 of g of x is 3, then the limit of the product is just the product of the limiting values. That's all you've got to do in this question. And so you can just say, well, it's -1 times 3, and you get your answer of -3. And I know what you're thinking. You're thinking, wow, that was not very fun. No, it's not. Again, this is the worst section in the entire book, so it all is uphill from this section. In the next one, they're telling me that the limit as x approaches 3 of g of x is -2. And then they tell us to simplify, well, what's the limit as x approaches 3 of g of x over x squared? And so we already know that the numerator is the limit of g of x, which we know is -2. The denominator is x squared, so you can say, well, you're going to be plugging the 3 in for that. So I get -2 for the numerator. I plug, notice it says x goes to 3, so you just plug a 3 in for x in the denominator. We get 3 squared. I get -2 over 9. Now, the last question it basically asks, I believe, a yes or no question. I'll go to it in a minute. But it's asking us something similar to, can the quotient law be applied to evaluate the fractional function, the limit as x approaches 0 of the sine of x over the cosine of 2x? Okay, so whenever you're saying the quotient law, well, what's the quotient law? The quotient law just means, just like I did here in number 8, for example, the limit as at t approaches 5 of this, if I'm using the quotient law, means I can just plug the 5 into the numerator, plug the 5 into the denominator, and get my answer. Well, can I do that in this problem? And when could I not do it? Well, the only time you couldn't do it would be if the fraction is undefined. What's going to cause the fraction to be undefined? A 0 in the denominator. So when I'm looking at this one and saying, well, if I try to plug a 0 in for x, I'm going to get the cosine of 0. But the cosine of 0 is 1. So this fraction is no problem. I can certainly apply the quotient law and just plug the 0 in. I would get the sine of 0 is 0 over the cosine of 0 is 1. This answer would be 0 over 1, or just a 0. So as x approaches 0, this function would approach 0. And so then I can say, well, yeah, this quotient law can be applied because the fraction exists. And again, the way you understand the fraction exists is simply the denominator. If it's anything other than 0, then the quotient law can be applied. And in this case, it was a 1. And so you can see it just says quotient law can be applied or quotient law cannot be applied. It doesn't even ask for an answer, as far as the answer to this question would also be 0. All right, so that concludes the worst homework section of the semester. We'll move on and improve the topics in the next section. I believe it's looking at continuity of functions. Pretty cool stuff. But then we're quickly headed into the later sections in chapter 2, and then into chapter 3, where we'll start the derivative techniques.